Um, so I'm Uma. I'm one of the co-founders of Succinct. We are working on making zk easy to use and accessible, and today I'm going to be talking about our zkVM SP1 and how it makes using zk in production easy, cheap, and really fast. So just to start off with, I think first it's worth noting that zk is really important to the future of blockchain scaling, infrastructure, and privacy. And I think in particular, a lot of the problems with like Ethereum that are being discussed right now, for example, fast finality between rollups, a lot of fragmentation, interoperability, bridging between ecosystems, I strongly think that zk is the only way that all of these problems are actually going to be solved. Verifiable computation is something that will help Ethereum scale. And because of this, because zk is the end game, I think in the next few years we'll see that every rollup will become a zk rollup, every bridge will become a zk bridge, and in general, all applications like oracles, coprocessors, etc. that can use zk will use zk because it's so powerful and such a good fit for the decentralization aspects of blockchain technology and actually scaling the overhead that comes with decentralization with this verifiable compute. But I think it's important to acknowledge that today, zk adoption has lagged behind. So it seems like this technology is really endgame, it's really powerful, but today, if you look at the top 2 rollups on Ethereum by TVL, they're all optimistic rollups. And then you have things like OP Stack that are being adopted by a bunch of changes in the ecosystem, and that is using optimistic technology, not zk. So why is it the case? Historically, zk has been really slow and really expensive, and that's a big reason that people haven't adopted it. So here's kind of a picture of a really beefy computer where all the cores are being utilized, people are about to run out of memory, and if you've ever built with zk before, you've probably encountered a situation like this, where if I want to run my zk prover, I have to spin up a really beefy AWS instance, and it still is really slow, and moreover, it's really expensive to use these things in production. I think what's even worse than being slow and expensive is that it's really hard for developers to actually use zk. So here's just a bunch of examples of random zk circuits written in languages like Circom, Ponky2, Cairo, Pill, and a bunch of math papers. And today, the state of zk is such that to make an end-to-end zk system, you have to basically have a cryptography PhD, you have to learn these arcane DSLs and SDKs, and then you have to code in these really weird languages and know the concept of what a circuit is. And so developing in zk is very, very difficult. And all these things combined mean that if you want to actually build a zk system that's used in production, it takes months, if not years. And we see this in Ethereum today, where a lot of the zk rollups took several years to go to production behind the optimistic rollups. And why is that? As I kind of mentioned, there's a very small number of developers who can actually write zk stuff and have the specialized expertise that's required. The developer velocity, even if you do have these expertise, is still really slow. You have all these custom languages with really primitive tooling. It feels like writing assembly. It's super unmaintainable. So for example, the Ethereum EVM has a hard fork around every 6 months to every year. And so if you want to build an L2 that's EVM compatible, you also have to upgrade your software every so often to keep compatibility. With zk, every time you want to do that, it's a really large engineering effort. Furthermore, when you have a zk system, it's not actually that customizable. So for example, if another team wants to use it and modify some small part of it to add a precompile or something like that, it's totally impossible for them to do so. And then finally, the audit surface area is really, really large. You have these code bases with hundreds of thousands of lines of code. It's really complicated cryptography and systems, and it's not really easily understood by many people. And even after that part, it's really hard to keep these things audited as you're upgrading these systems. So at Succinct, we were very familiar with all these problems. We had encountered a lot of them ourselves personally, building in the zk space. And we realized, like, for zk to reach its full potential, to go mainstream, the current developer experience and the current entire experience of using zk in production is totally broken. And so this is why we built SP1, our zkVM. Okay, so what is SP1? SP1 is an open source, general purpose, performant zkVM. So let's kind of unpack what all those things are. A general purpose zkVM means that you can just write normal Rust code and then use that code to get zero-knowledge proofs. Underneath the hood, how this works is we have Rust. It compiles to RISC-V, which is a standard target supported by the normal Rust compiler, so we didn't have to do any compiler work or anything like that. And then we prove that the RISC-V ISA with your particular RISC-V program executed correctly. Underneath the hood, for our proof system, we're using small field starts with fry and the log derivative lookup argument. And so the main point of being general purpose is that, again, you can just write normal code, and that's super powerful, and I'll get into more why that's such a big unlock later. The second important thing about SP1 is that it's extremely performant. So it doesn't matter if you're general purpose, if it's not actually practical to be used. But we've actually found that SP1's proving time and cost is actually better than the customized circuit world that I was describing earlier. Our team came up with several algorithmic innovations and a few clever tricks for really state-of-the-art performance for a zkVM. And then we have really strong performance-oriented engineering on both our CPU and GPU prover implementations. And then finally, SP1 is open source. So all our constraints are fully open source, it's MIT licensed, and that's really important for security and auditability. It's important to understand that we're actually proving the RISC-V ISA, like what are the security assumptions we have. It's also modifiable and customizable by external teams, and we've had a few external teams contribute their own precompiles and modify the system for their particular needs. Okay, so to dive into how easy SP1 makes zk, here's an example of a Fibonacci program written for SP1, and you'll notice that it looks very much like normal Rust code, which is the intention. With SP1, you can use the Rust standard library, so you can use Vex, you can use all that stuff from the standard library, so you can use Rust normally. You can reuse all the existing crates and libraries that you really want. So for example, you can use Serde, you can use JSON, you can use like the Tendermint library, you can use regex, you can use Rust crypto, you can use revm and ref, and that's really powerful for the reasons I'll describe later. And we've personally found that our developer productivity with SP1 is 100x, if not more, than the custom circuit era. You can use print statements, for loops, if statements, all those things were not available in kind of like older ZK languages because you had to write circuits. And then you can use all the Rust tooling. And all the programs written with SP1 are really easily maintainable and customizable because it just uses normal Rust. So you don't need any specialized expertise. Any Rust developer can use SP1. And one really powerful thing about being able to reuse existing crates and libraries like revm and ref is that because of this code reuse, the audit surface area is much smaller. So for example, ref recently is this Rust Ethereum node implementation by Paradigm, and they recently got audited. And so that's thousands of lines of code that we can just import, and we don't have to audit it. We can import ref and write a zkEVM state transition function and reuse their existing audit and the fact that they're used across a bunch of different ecosystems. So the security story behind programs written with SP1 is also a lot better. So overall with SP1, using zk, instead of taking months and years, becomes a weekend project. And it looks very normal, which is the intention. As I also mentioned, SP1 makes zk really performant, which was like another big blocker to zk adoption today. We have a bunch of algorithmic innovations for our state-of-the-art performance versus other zkVMs. There's a lot to get into there. I could probably spend hours talking about it, but to go over some of them, we use this novel offline memory checking argument. We have this concept, we make heavy use of lookups. We have this multi-table setup, so there's certain RISC-V instructions that are very complicated to prove and cost a lot of proving overhead, but you only pay for them when you actually use them, and a bunch of other techniques. One of our main innovations was this precompile-centric architecture, which is actually pretty hard to get working in a zkVM, that was motivated by this key insight that for most blockchain applications, for example, a roll-up state transition function or bridging, most of the prover overhead comes from things like hash functions and signature verification. And those usually take a lot of cycles in a zkVM. So for example, in RISC-V, when you compile a catch-app, hash function naively, it might take 10,000 cycles, which is quite a lot. What we do is we have this precompile system, which you can kind of think of as like ZK native assembly, where we have a specialized circuit for these hash functions and signature schemes, and then it talks to our main CPU via a lookup argument, And what that does is it makes the raw cycle count of a particular computation go down a lot, often by an order of magnitude. So I have this table that kind of shows a bunch of different programs with their cycle counts, and you can see when we add our precompiles, the cycle counts go down by a factor of 5 to sometimes even 10. And that means that your proving time just went down by 5 to 10x by using our precompile system. So SP1 in general is around like an order of magnitude, sometimes more faster than other zkVMs, and a lot of that comes from this precompiles that we support. More recently, we've been working on SP1 GPU, which is a GPU implementation of our prover. Proving, especially with Starks and Fry, is a really parallel workload. There's a lot of hashing that can be done in parallel, and other parts of the operation are also very easily parallelizable. And we found that the GPU implementation of our prover improves latency and cost by 5 to 10x as well. And so with SP1, ZK is now not only super easy, but also really performant. So in all, SP1 just lets developers write really normal code, and you don't have to sacrifice performance. So it's kind of like the best of all worlds. And I have a particular example that our company actually went through to kind of show you and demonstrate the before era of ZK and the after era of ZK with SP1. So our company, when we started off, we were working on ZK bridging, and we spent a bunch of time implementing a specialized ZK circuit for verifying the Tendermint consensus protocol. And so this is an example of the kind of like code that we had to write. You can see it's very confusing. It's very ugly. It doesn't look like normal Rust. There's this like specialized DSL that we have. And this is just to calculate a sum in a ZK circuit. So this was pre-SP1, the kind of pain that people had to go through. And by the way, this is just like a few lines of code from a file. There's actually a huge folder full of a bunch of different files that in total is thousands of lines of code to get a Tendermint-like client working in ZK with circuits. Now with SP1, we made a Tendermint-like client, and actually I can show you all the code on the right. It's kind of small, but it ends up, you can see here, there's line counts on the left-hand side of that, and you can see it ends up being like 60 lines of code, but Spaces is probably a lot less. And I'm just going to go through it piece by piece and show you like how magical the experience of using SP1 is. So you can see that first, at the top, we just import a bunch of libraries. So we import this Tendermint-like client verifier library. That's not a library our team wrote. It's maintained by an external Cosmos team, and we can just import it. It's already audited. It's used in a bunch of different places. We just import it. It just works. And then we import the ally library, which is maintained by the ref team and is useful for doing stuff with Solidity and Solidity types. Then the main body of the function that's actually verifying the Tendermint like consensus that enough validators or 2/3 of the validators have signed is just in this very small 20 lines of code. All we do is we read in 2 different blocks. We use Serde to decode them into the appropriate struct. We instantiate a verifier from the Tendermint library, and then we just call the function verify update header that verifies enough validators have signed off, and that's all there is to it. We don't even necessarily need to understand like what's going on behind the scenes. We just know that this is a good library for verifying Tendermint. It's already been audited, it's used, and it's really simple to use in SP1. It's just 20 lines of code. And then finally, we take the 2 headers, we hash them, and then we turn it into the Solidity struct, we ABI encode it, and then we expose it as a public output of SP1 so that we can use it on-chain on Ethereum. So if you look at these 2 things side by side, on the left-hand side you have the custom circuit Tendermint-like client that we built. I took 3 very hardworking, smart engineers on our team 5 months to build this end-to-end. The final lines of code I think was around like 8,000 lines of like audit code. We spent several $100K getting this system audited. It took 1.5 months, and it's like extremely complex. There was a bunch of other teams that wanted to use it, and we tried to give them the code. It was open source, but they had a really hard time figuring out how to modify it. With SP1 Tendermint, it took 1 engineer, I think it was actually our intern, 3 hours of work. It's 50 lines of code, as you guys saw. There's barely anything to audit, probably like 1 day, if that. And it's extremely simple, super forkable, and customizable. We hosted an SP1 Tendermint workshop. 50 teams showed up, and now I think there's dozens of people who are working with forked versions of SP1 Tendermint, customizing it for their own use case, because there's a lot of different Cosmos chains or Comet BFT-based chains that want to use it. And yeah, it's very easy for them because it's just normal Rust code. Now the thing that was really surprising to me even was that in our old system, we'd spent a lot of time and effort really optimizing it. And in the end, we got the proof latency to be down to around 10 minutes. And we were really proud of this achievement. And the proof cost was a few dollars. So in all, I think we were pretty happy with that. And then with SP1, a big question was, well, the developer experience is so great, but surely maybe that comes at some cost. But in the end, we found with SP1 actually that the latency when you run SP1 GPU ends up being 2 minutes, and the proof cost is actually pennies. It's much cheaper. And so it seems like SP1 is just strictly better in every way. You have a really nice developer experience, it's really easy to customize, the lines of code is really minimal, and the latency and cost of proving is actually way cheaper. It almost seems too good to be true. And I think one big lesson we learned from this is that because SP1 is so general, you can use it for rollups, you can use it for bridges, you can really write any program that you want to use zk for on top of it. For us, it's much easier to optimize it and justify the engineering overhead into writing an SP1 GPU prover, really optimize how we set up our cluster on AWS, and then find every single bottleneck and performance optimize it to the fullest extent possible. For example, in our Plonky 2 circuit world, it wouldn't have made sense from an engineering ROI perspective to put that prover on a GPU because it's only one use case, and then how many people are going to use it, it's really hard to customize. And so because SP1 is so general purpose, we can actually get much better performance and cost than more special purpose zk systems, which was a really surprising insight, even to me. Another example that I want to briefly touch on is that you can use SP1 for tenorment and bridging, but you can also use it for rollups. So currently, a lot of the zk rollups are kind of the custom circuit version of the world that I described, where you have these teams that spend a lot of time and effort writing these custom circuits for proving an EVM state transition function. With SP1, you can just take ref, you can import ref, and then get it working within SP1. It takes around a weekend. And then the surprising thing actually is that the proving cost per transaction is still pretty practical. So this is actually in a pre-GPU world. These numbers were run on our CPU prover. And so with the GPU prover, the costs only get better by like a factor of 5 to 10. But the proving cost per transaction for average Ethereum blocks ends up being between 1 to 2 cents, which is already pretty practical, especially given that rollups are already paying Ethereum a similar amount for DA and settlement. And so it points to the fact that the future of kind of zk EVMs and rollups in general is something that would be SP1 based and not the custom circuits that we're used to for today. So our hope is with SP1, now that zk is really, really easy, it's like a weekend project, it's also cheap and fast, that now we finally have all the tools in our toolbox to make zk go mainstream. Now developers can experiment freely, and their number of developers who are able to use zk is 100x bigger. And so we hope that every rollup team, all bridges, and all the kind of applications that I highlighted earlier are now able to use zk in the way that it's meant to be used. And then the last thing I want to touch on that a lot of people ask me is like, okay, this sounds really awesome, when can I actually use it? And so we recently completed around 4 audits, including a public audit competition that would, anyone in the world could participate in for a large bounty. And we just finished that up, and we're launching mainnet production-ready verifiers in the next few weeks. You can already use it on testnet today. And from day one, we have a few top teams using it for real production use cases, like the rollups and the bridging that we're excited to highlight when SP1 goes live. So yeah, you can get started building with it today, and then use it in prod in a few weeks. And there's my contact information if you have any questions. Cool, that's all.
I actually have one question here. Because we all know SP1 can be used for zk rollups, bridging, etc. I don't know if there are already projects like DeFi projects, gaming projects experimenting with SP1 as this extremely productive and general purpose.
Yeah, today I would say the one big category is bridging. So for example, we work with teams like Celestia and Avail that are these kind of next generation L1 DA layers, and their bridge to Ethereum, because they're often used for Ethereum rollups, uses SP1. Polygon's Aglair is also being built with SP1, so that's used for like interoperability and for like rollup interoperability. We've integrated with like a few rollups, like for example Tyco and Sovereign SDK, and we're working on a few other ones to have SP1 have full zk validity proofs for all those rollups. Yeah, those are like the big categories.
Got it. Yeah, and also for the SP1 ref, what's the main difference between SP1 ref and Iris0's ref before?
Yeah, I think they're pretty similar. Like it's just importing existing Rust code to get a zkEVM state transition function. For us, we did some work on the ref side to actually get it to compile within SP1 because there's like some crates that won't work within SP1 if you want to talk to your file system and stuff like that. So you have to do some minor refactors. Our repo ends up being like very, very small. It's like 500 lines of code. Yeah, that's the main difference, but I think it accomplishes the same kind of functionality.
Yeah, more questions for Joe.
So how hard it is for like another L1 to produce like a library like the one that you showed that Tendermint has? Is it like a big lift?
No, like if you already have a Rust version of whatever you want to prove, like if you have Rust code for your program, it's really easy. Like you just import your library and you write your program within SP1. If you don't have Rust code, Rust is like currently our best supported language, so it's like pretty important that you'd have to take your existing code and like write it in Rust.
Cool. Yeah.
How abstract are the interfaces to the backend? Like, how dependent is SP1 on Plonky 3?
How dependent is SP1 on Plonky 3? I would say that our proof system there's a lot of different components of it. So there's like the actual proof system, which is Starks and Fry. Then there's like our lookup argument. That's actually like totally separate from Plonky 3. It's like implemented. It's kind of another layer. And then there's like also our whole recursion stack, which is like totally within SP1. It's like totally its own thing. I would say for Plonky 3 provides a really, really great, really optimized like Fry implementation that we use. And so for us, like the Fry implementation is pretty tied to our recursion system, so it'd be hard to move to like a different Fry implementation. But so I think moving to a different backend would be like a very significant change. But we are also experimenting with like upgrades to our proof system for improved performance in like future versions of SP1, so like SP2 or something like that. But it is like a very significant change.
Cool. Any more questions? If no, then thank you. And we'll have our last speaker for the infrastructure side as a founder of Delta talking about